Okay, so that were the trends. How can we model seasonality? Well, so there was some discussion in the literature whether neural networks can model seasonality directly or not. Some early work suggests they can model it. Later, some works they said, well, we have to deseasonalize the series before we feed them into the neural networks. We did some work in that space as well, where I mean it's kind of obvious, right? So the machine learning model can learn a seasonality if you have enough data, right? So I mean, just think about a simple experiment. You generate a sine wave and you let the neural network learn that sine wave. Well, how many periods of that sine wave do you need until the neural network really got it and predicts it confidently forward? One period is certainly not enough. Do you need 2 periods? Do you need 20 periods? Well, exactly. So neural networks can learn seasonality. They can learn it across time series, obviously, but sometimes if you don't have enough data, if your data set is small and so on, or the seasonality is quite varied, then deseasonalisation can help. And another very important point is that the assumption in forecasting is usually that we know the seasonality beforehand and that we can confidently extrapolate it infinitely into the future, right? So if I say 10 years from now, a Monday will still be a weekday and Saturday, Sunday will still be weekend, and electricity consumption will still be the case that on the weekend people don't go to work and, do different things. I mean, of course, you could say, well, I don't know, in a Muslim country, the weekend is on a Friday. And so you could have the hypothetical situation that one country changes their weekend from being Saturday, Sunday to now being Friday, Saturday, right? But that's very hypothetical. So these changes in seasonality, we don't assume them to happen, right? So the seasonality, we extrapolate it confidently into the future, and we also know it beforehand. So very often I see these machine learning papers that say, oh, and we can automatically learn the seasonality, and we have these great attention mechanisms that now learn the long-term patterns in the series. And it's like, yeah, well, but the long-term patterns in your series, that's only trend and seasonality, and the seasonality component, you don't have to learn that with an attention mechanism. I can just tell you what the seasonality is, right? That's a bit the idea. Okay, so how do we model seasonality? Well, we can have seasonal indicator variables. So we can have a categorical variable in our data set that tells me Monday, Tuesday, Wednesday, and so on. We can do that in a one hot encoded way. That's what forecasters would call a seasonal dummy variable. So you have a variable that tells you, you have a feature that tells you Monday, and then you say 0, 0, 0. Oh, here's a Monday. Okay, like one hot encoded, just which instance is a Monday. Yeah. Now, well, I mean, or let's say you do that as a numeric feature, right? So let's say 0 is a Saturday, 1 is a Monday, 2 is a Tuesday, and so on. So you have this feature that runs from 0 to, in this case, 50. So that's probably like the weeks, right? So we are, in this example, we are counting the weeks. Still doesn't quite fit, right? Because it drops down at about 40 something. But okay. But you see that you get the idea. So the idea is 0 is a Sunday, 1 is a Monday, 2 is a Tuesday, and then you get to the Saturday, which would be a 7. And then after the 7 comes another Sunday, which is a 0, right? So here Sunday, Saturday, and now the next value is again a Sunday, and that's how you go through the week. Okay. Yeah, so now you have this problem that you have these very abrupt changes. And yeah, for example, Saturday is now way closer to a Wednesday than to a Sunday, right? If you say, here's my Wednesday, now obviously this is a lot closer than this. So if you do that, it looks like that if your Saturday is way closer to the Wednesday than to the Sunday, which is not what really happens. Saturday and Sunday are only one day from each other, not 3 days like Wednesday, for example. Yeah, so the idea is, well, let's do that a bit more smooth, and this is what is now called Fourier terms, right? So the idea is, well, if I have this cycle, right? I mean, maybe you've also heard of polar coordinates. So the idea is, I have a clock, and that clock goes round, and you could obviously think of, well, I have a clock that is the whole week, so Sunday is on the top, so we go around, then 1 week is over, and then we go again. So the way to model that is you just get a sine wave and a cosine wave, and they together can model you exactly so they can identify uniquely each point in the cycle, right? So the sine alone is not enough. If you look at the sine, for example, you have here 2 values that are the same, even though there are different points in the cycle. But sine and the cosine alone, obviously same thing, right? Here. But sine and cosine together, they are able to identify each point uniquely in the cycle, and they are smooth, right? So now it's really, you don't have this abrupt drop which makes that points that are near each other appear to be far from each other. That doesn't happen anymore. Yeah, so that's called Fourier terms. I mean, you can look at, for example, at the FPP book, Hindman and Athanasopoulos. Well, I cite here the 2018 version, but there are obviously newer versions. Yeah, the way you define it is with this formula sine 2 pi kt divided by s, and then the cosine of the same thing. So t is the time point, s is the seasonal periodicity, k is the number of sine and cosine pairs used with the transformation. And yeah, so the number of Fourier terms, so you would usually not have only one sine wave and one cosine wave that has exactly the correct wavelengths, but you would also use kind of higher, so for example, here we have exactly one cycle, right? But you could obviously also kind of go to 2 cycles in that same time frame. And if you do that, then, well, you control the smoothness of the seasonal pattern. So Fourier terms, people would usually use not only one sine one cosine wave, but more, couple of them. Okay, yeah. Another way to deal with, one way to deal with seasonality would be, you have these additional features, Fourier terms, that tell you where in the cycle you are. Another idea is you just, deseasonalize your data. How would you do that? You use STL, or you can use MSTL, which is just a multiplicative extension of STL, or there is a method called STR, seasonal. So STL is seasonal trend decomposition using low S, STR, seasonal trend decomposition with regression. So you have your data, you extract trends, and then different seasonality components, and then whatever is left is a remainder. So you can now, for example, deseasonalize and then only feed the trend and the remainder component into your machine learning algorithm. you can see that as a form of boosting, where you have a weak learner to model the seasonality, and then the machine learning model trains on the residuals. Yeah, so what you effectively do is you put expert knowledge into your model. About the seasonality, and again, this works well if you don't have enough data to just really model that seasonality directly with your machine learning model, or if the seasonal components are very different between the series. Here I give you an example. If you look at M3, M4, seasonalities are kind of all over the place. CIF as well. But then you look at something like the NN5 data set, well, all the series have actually the same seasonality, right? So, and now think about a forecasting problem. Let's say you are forecasting products in a business. Many of these products will have exactly the same seasonal pattern, right? So all the sunglasses in a certain country, well, depending on the size of the country, but let's say you are in a European country, all the sunglasses sales will be high in summer and low in winter, right? Whereas you come to Australia, sunglasses sales in the north are all year round the same, and in the south they are higher in summer than in winter, but obviously summer in Australia is when winter is in Europe, so of course you can get like opposite patterns and so on, but if you have a data set where the seasonality is the same across all the series, you can easily just train that with your neural network. And then these M3, M4 data sets, as they are kind of a bit artificial in a way. Nobody has a data set like that and wants to forecast it. There, people had to do different things to just accommodate these very different seasonalities, and in that case it can be quite sensible to deseasonalize before you run your neural network, right? For example, the CIF competition, the method that won that by Slavik Smil, he decomposed the series and then ran the RNN just on the remainder of the series, and that worked well because, as you see here, seasonalities are all over the place. Otherwise, if this was the data set, you would probably just put in some Fourier terms into your model and learn it. Okay, some further considerations about seasonality. Yeah, as I said, M3 and M4 data sets have very different types of seasonalities mixed together. Series are not aligned. In the M4 global models were heavily customized for this particularity of the data set. For example, the winner ESRNN models the seasonality for each series separately. In real-world data sets, this will normally not be the case. Seasonal indicators and Fourier terms, they do need aligned series, right? And in real-world data sets with enough data, seasonal indicators and Fourier terms will usually work better than deseasonalisation. That now also, so when you now really deploy such a model, that's something you need to keep in mind, right? So because the Fourier terms, they need to be synchronized, right, across all your, like if you say, this is my weekly seasonality, now all your series need to say, okay, if this is Saturday and Sunday, well, all the series need to be aligned. And now also when you now later deploy your model, right? So let's say you train your model on a training set, you test it on a test data set. Now you go to deployment. Well, also for the deployment, these Fourier terms need to be aligned with whatever you did during your training. So you usually need to choose some starting point, Unix time, 1970 is your starting point that you use for training and for deployment to synchronize your Fourier terms and things like that.